Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of CUDA Crash Course, we're going to be going on and talking a little bit about profiling in terms of using the time function called clock within CUDA. Right, so a lot of times we want to get some fine-grained information about how our code is actually executing, and especially we want to figure out sometimes, how is our work balanced across the system, right? And this can be, how much work is really being done by each thread block. Right, and one way we can do this is using the clock function, right? So the clock function, this is coming from the CUDA toolkit documentation, right? So it says when executing device code, it returns the value of the per multiprocessor counter that is incremented every clock cycle, right? So what we end up doing is we'll take a clock cycle count at the beginning of execution, and then another at the end of execution. We'll take the difference of those, and that will give us basically the elapsed number of clocks. So a good example to do this with is sum reduction. So as we talked about in our sum reduction series, we did quite a few optimizations to better balance the work that's being done by this kernel, right? And so one of the problems that we had early on was the fact that earlier thread blocks were doing more work than later thread blocks, right? And so this is we can think about this intuitively in terms of we start by every single thread block is doing reductions, and then only half of them are doing reductions, and then half of that original half or that next half is doing reductions, right? And so we're basically getting rid of the number of threads is decreasing by half every single iteration, right? And so what this leads to is some thread blocks taking longer than other thread blocks, right? So this is a good candidate if we want to kind of visualize this for doing this kind of timing, right? And profiling. So here's our basic sum reduction kernel. It has a couple modifications. So this came from the bank conflict optimization. So we got rid of the bank conflicts in shared memory, but it's still we haven't done any kind of work packing yet. So what we see here is that at the very beginning of execution, what we'll do is only the first thread needs to do this inside of a thread block, because what we care about is when an entire thread block finishes. So here, right, only thread 0, we'll go ahead and update this clock, right? So we'll pass in this clock t. Now the alternative is we could use clock 64, and this we'd have to use a long int. But for this one, we'll just use clock t. So here, in order to get this cycle count, right, all we need to do is call clock, right? And then again, we'll do this at the very end of execution for each thread block, right? And we'll call this again. Now at the very end of our kernel, right? So if you remember how we implemented this last time, it basically took 2 launches, right? We did, the majority of the work in this first sum reduction call, and then we only had a single thread block in our next call. So we really are only going to consider the results or the timing from the first call, because there's multiple thread blocks to compare against, right? And then over here at the very bottom, we'll go ahead and print out, separated by a comma, the block number, and then also the time, right, or the number of clocks, right? And this is just going to be time I plus grid size, right? So we'll take the later time or the later clock count subtracted by the earlier clock count. Now we have to be careful depending on what we're timing inside of our code, because if we have some long-running code, we might the counters might actually overflow and loop back around. Right, and if this happens, we're not going to get any useful results. So we have to make sure that what we're actually trying to clock, right, is of reasonable size. Right, we can't, if we have some GPU application that runs for a week, right, we of course aren't going to be able to really capture that in a meaningful way, right? So let's go ahead and look at. Let's go ahead and see what happens, right, running this. So we'll just compile it as normal. So nvcc-o. Sum reduction.cu, right? And then we can go ahead and run this, right? And so you see that we get these cycle counts, and as you can see as a general trend. Now we have to keep in mind that we're not actually guaranteed how threads are going to be scheduled. We've got a rough idea in terms of how threads will be assigned, but there's going to be variation from launch to launch in terms of what these values are. So as you can see, we have 3855, 3810 cycles, but if we run it again, go back up to the top, right, we end up getting 3817, 3408, so it'll change between launches. But we can take this information, I just threw it into a spreadsheet real quick to generate a quick plot. And we can start trying to figure out, larger order details. And, what we can see is that these earlier thread blocks, especially these first 50 or so, they end up staying on the GPU and doing a lot more work, or taking up, significantly more cycles, almost double in some cases when we look at, these around the 25 to 50 mark, right? Then later ones at the closer towards, the end of our actual grid. So just around 256 or so. So this can be a useful profiling tool, and it's fairly easy to implement, right? So we just end up doing a copy in, and then we just call clock a couple times. And so this can be, a good way to profile things. But that's going to go ahead and do it for this episode. As always, check out any of this code at github.com/coffeebeforearch, right? So this is all in the CUDA programming repository. This one's under miscellaneous, so we've been going over a lot of kind of utility stuff, including, device querying. So here's our clock example for sum reduction. So again, feel free to check this out. Also feel free to, I'll go ahead and link this spreadsheet. So in this spreadsheet, we have a comparison of, say, our different implementations of matrix multiplication, as well as our different implementations of sum reduction that we did. So this is probably more relevant here. So right, this is on 2 to the 20 elements. So, you can see based upon, or rather this is from 2 to the 8 elements to 2 to the 20 elements. So you can see how each of these scales, right? So the one that we're running in this example is this yellow line right here. So this no bank conflicts one. But yeah, feel free to check that out. Feel free to check me out on Twitter at AcceleratorNick. If you have any questions, feel free to let me know, or if any requests for other videos that you'd like. But as always, I'm Nick, and I hope you have a nice day.